Alright, good morning, good afternoon, good evening class. This is Mr. Arosena, and today in physics we're going to be talking about vectors at an angle. So the last couple of days we've been talking about how to work with vectors, and it all basically broke down into turning every vector into an x and y component and then working with it from there. Today is going to be really no different when working with vectors at an angle. The reason we're doing it slightly differently today, though, is that sometimes one of the components is more useful than the others, as you'll see in a couple of the examples we'll do today. All right, so here's the first example. So here, we want to know what is the magnitude of the useful force that's being applied in this particular situation. Okay, so notice that the person pulling the block of ice is applying a force, and what this force is being applied at an angle of 25 degrees. Okay, and notice I haven't put any numbers in for the force, and that's okay because we don't actually need to know. We just need to know what is the magnitude of the useful force. Okay, so the numbers don't actually matter too much. If we can do this without numbers, then we can do it with numbers later on. All right, so to resolve this, he's pushing or pulling this block of ice in this direction. Okay, so the useful force that's being applied, so notice again, we can break this, let me just erase some of this, erase this. We can always turn this force into an x component and then a y component, like that, right? We did this a lot last week. So since this force is acting at an angle and has two components, one of these components is going to be more useful than the other when determining how fast he's pulling this block. Okay? In this case, since we're moving in this direction to the right, it makes sense to say then that the x component is the more useful one. Okay, so this x component here is the useful force, because it's the force it's the part of the force that's actually pulling the block of ice to the right. The y component part's not doing any of the pulling to the right. It's actually trying to pull the block up. And if this y component was big enough, the block would actually be pulled in an upward direction, in addition to being pulled to the right. In this case, we'll assume that the y force isn't big enough to lift the block off the ground, because that doesn't make any sense. Anyway, so if the useful force is the x part, then we can say the following, that the useful force is the x component, and we just have to calculate what the x component is. Well, the x component, I'll redraw my triangle. There's the force, and then the x component, here's 25 degrees. There's the x component, there's the y component. To find the x component, well, this is just a right triangle. We're going to find the x component. This is the adjacent side to the angle. So we'll use the CAH part of SOHCAHTOA. So we can say cosine 25 is equal to the opposite side over the hypotenuse. So we can say then that if I multiply both sides by f, that'll cancel out the forces. So then force times cos 25 will equal the useful force. There we go. There. So this is my useful force. Oops, I shouldn't point at that. There we go. Say there. This x, this is my useful force. Useful force. In this situation, okay, if the block was moving in an upward direction, then we would have to calculate the y component. There you go. So there's another use of vector components, is that we can use this to figure out which one is actually useful, which part of the force is actually useful. Okay. It'll actually turn out in the next unit, this will actually become quite important because well, we'll see in the next unit. So being able to figure out which force is actually being used, that will become important in the next unit. All right, on to the next example. Okay, example 2, and here's one that you may have encountered, maybe not recently, but definitely in the summer you'll encounter something like this when you're mowing your lawn, or if you have a push lawnmower at least. If you have a ride-on lawnmower, you won't notice this at all. All right. So here's an example. This person is pushing down on the block of ice this time. Let's actually give him a force. We'll need this force. So let's say he's pushing down at 200 newtons, and we need a weight or a mass for this. I'll just give it to you in newtons. So we have a 100 newton force going down. Okay, and let's make this friction. Let's not just give this a little bit of friction. Mu, let's say 0.2. All right. So we want to know what is the net force. Now right away, you can sort of start this similarly to the last one, is we can figure out which part is actually going to be pushing this thing. So that'll be this part, the x component. And then here's the y component down here. Okay, so we'll start this off similar to how we did the last one. Okay, so here's the useful force. We'll calculate the useful force. Okay, and I'll just pull the formula from the last slide, where it was x. The x component was the amount of force times cosine of the angle. In this case, it's still 25 degrees because we still have an angle of 25 degrees. So this will be, let's see, x equals 200 times cosine 25. Let's pull this up on a calculator. So 200 times 25 cosine. Find the right mode. Oh, wait, I think I messed that up. 25 cosine. Clear all. 25 cosine times 200. Yeah, so 181 newtons. Oops. So the useful component is 181.3 newtons. Okay. So that's my useful force. Now you might think right away that, okay, if this is my useful force, that must be the net force, but you'd be wrong because we actually have a force of friction to worry about. So there will be some amount of friction pulling back this way. So there will be a force of friction pulling us, or opposing our 181.3 newtons. How big is that force of friction? Well, if you remember from a few days ago, you can calculate force of friction as mu times Fn. And what did I say Fn was? Fn was the amount of force compressing the two surfaces together. So we already know that we have a 100 Newton force pressing down, but is there anything else pressing this thing down? Okay. If you have a few moments to think about that, you can actually pause the video here and just think about it. And then when you've figured out what else is pressing down, you can start the video again. All right. If you figured it out, or if you haven't, there is a second force pressing down, and that's this y component. This y component is going in this downward direction, right? So the normal force is then now slightly bigger. You have your mu, and the normal force is going to be the force of gravity plus that y component, because that force of gravity is already pressing down, and then this extra y component is also pressing down. So now we can say the following. Okay, so mu, so this will be 0.2. We know the force of gravity is already 100. And how do I go about calculating this y component? Well, the y component, if I use SOHCAHTOA, the y component will look like this. So SOHCAHTOA we'll use this part of SOHCAHTOA. So we can say sine 25 is equal to the opposite side of this angle is y. So y is now the opposite side, divided by the force of 200 newtons. There we go. So then y is just going to be 200 times sine 25. And I'll show you guys that. So multiply both sides by 200. 200's cancel out. Y is equal to 200 sine 25. So this will end up being, so, oops, not 25 sine times 200. So there you go. About 84.5 newtons. 84.5 newtons. All right, now we can put that into here, to my force of friction equation, 84.5 newtons. Calculate this all up. So we got 0.2 times bracket 100 plus 84.5. Close my bracket. Equals 36.9 newtons is my force of friction. 36.9 newtons. Right, now we know how much friction is opposing us. We know how much force is useful, so we can calculate the net force. The net force will just be the useful force that we're applying, 183.9 newtons, minus the force of friction, which is 36.9 newtons, and that gives us altogether 181.3 minus 36.9, 144.4 newtons. 0.4 newtons. There. So by the act of pushing down on this block to move it, we actually generate slightly less force. Yeah. Assuming the surface has some friction. If the surface is frictionless, then it doesn't matter because we don't. The only force, yeah, there's no friction, so the force of friction is non-existent. But that's hardly ever the case. Hey, so there you go. So using the components is quite helpful in determining certain things. So this is why, like, if you've ever pushed down on a lawnmower, it's a little harder to move than if you are pulling up on it. Right? And it's the same is true for anything. If you're moving an object, try not to push down on it. You're actually going to make slightly more force or more work for yourself. All right. All right, on the next example. All right, so here, what is the magnitude of the force that pulls the box down the slope? So here's a force that's at an angle. Okay. So we want to know what is the magnitude of the force that is pulling it down the slope. So this part. Okay. Now, I don't have any numbers here, but that's okay because we don't need them yet. One thing we will say though is that we need to know the forces acting on here. We'll ignore the person for now. So I'll just cross out this person. We'll ignore the person because the person doesn't matter. But we want to know. So here is my force of gravity. Alright, we want to know how big is this force sliding down. Well, interestingly enough, I'm going to erase that arrow for now. Erase this one. Interestingly enough, when you encounter a problem like this force of gravity, if you were to look at it and consider the slope, this force of gravity can be broken down into two parts. Now, normally we would break down our vectors into x and y components, but since gravity always points down, it doesn't make sense for this. So instead what we're going to do is we're going to break this force of gravity down into a component that compresses against the surface, like this. Okay, compresses against the surface, and then a component that slides down the hill like this. Okay, so that's what the force of gravity will break down into. Okay, and it's sort of like if you were to, let's see, I think it'll look like this. There we go. If I were to rotate this, you'll see this. Hopefully you can see it. If I were to rotate the picture like this, so that the slope is horizontal. There we go. Let's scale it up a bit so you can see better. There we go. So as you can see, the force of gravity can act as effectively a vector at an angle. Now the interesting thing is, how do I figure out what either this angle is or what this angle is? Okay. Well, let's figure that out. Let's see if I can get a. Let me erase all this first. And let's start from a fresh picture. Alright, so I'm gonna rotate this so it's like straight. Scale, zoom in a bit so it looks a little better. There we go. Alright, so I'm gonna extend the force of gravity line. Force of gravity will go from here going to here, like this. There we go. Oh, let's change that color so it's easier to see. Alright, so the force of gravity goes like this. And I'll do that. Okay, then I will draw the components in blue. So you have one component going straight down. I'll draw it to about here, I guess. Something like that. One component going straight across like that. Alright, there you go. Now, a little bit of angle math from earlier math classes. If it's drawn like this side or this line and this line are parallel to each other. And if they're parallel to each other, it means that this angle and this angle must be 20 degrees. Okay, so what does that mean? Well, if those are 20 degrees and we've drawn this gravity line so that's perpendicular to here, this means then that this angle over here is 70 degrees, and that makes this angle here also 20 degrees. So there we go. So that's 20 degrees. Now, why is that important? Well, that allows us to easily calculate this component pressing down and this component going along the slope. Okay. And the reason why I labeled all three angles, because you could easily do it with a 70-degree angle, is because this angle and this angle are the same. Okay, so this is to show you that this angle and this angle are the same. And why is that important? Because it makes it easier to remember the next step. So this component here, this is the part that is compressing against the floor. So this is the compressing component. Compressing force against slope. Against the slope. Okay, and to calculate this compressing force, we use, if you look at this side, this compressing force is the adjacent side to this 20-degree angle. So we can say then the compressing force, and we'll call it force compress. Force compress is going to be, if I use SOHCAHTOA, the force compress over the force of gravity, because I'll relabel that this line here is the force of gravity, which makes the hypotenuse of our triangle. The force compress is going to be equal to cosine theta, okay, because theta is this angle and also happens to be the angle of the slope. And if you rearrange this equation, you get the following. The force compress, the compressing force is equivalent to the force of gravity times cosine theta. Okay, there you go. And then now you can sort of see why I've decided to use this 20-degree angle instead of the 70-degree angle, because it's easy to remember then. Compressing force, cosine. Compressing force, cosine. So very easy to remember, right? I hope so, at least. All right, now this other force here, this short one here, this is the sliding force, because that's a force that, force, I call it sliding force, that's what we can call it, sliding force. Because why do we call it the sliding force? Because that's the force that is causing the box to slide down the slope, all right? So sliding force down slope. right? And then to calculate the sliding force, well, this is just the opposite side, so we can say the sliding force over the force of gravity is equal to sine theta. And then when we rearrange this equation, we get sliding force down the slope is equal to Fg sine theta. There we go. There. And just like the compressing force is equal to, is using the cosine, sliding force uses sine. So compressing force uses cosine, sliding force uses sine. There you go. And I think we answered our question, because our question was just asking us what is the magnitude of the force that pulls the box down the slope. Well, that's just this formula here. So sliding force equals Fg sine theta. Okay. So anytime we need to find out how much force is causing the box to slide down, we'll use this formula, Fg sine theta. If I need to know how much force is compressing the box to the slope, we'll use this formula, Fg cos theta. Okay. And there we go. All right, I think one last example. Now, here's one that sort of uses the two components of the previous example, and now you have to ask yourself or figure out how much or how big must the coefficient of friction be if this box is to remain stationary. Okay, and for this, we're going to analyze it in a couple of ways. All right, so we know that if there's nothing working against the box, we're going to have a force that is going to compress or cause it to go down the slope. That's my F slide, right, from the previous example, F slide. Okay, so this one's easy enough to calculate. So F slide equals, from the previous example was just Fg sine theta. So Fg, mass times gravity, so 3 times 9.8 times sine 35. Plop that into our calculator. Oops, where's my calculator? There we go. So 3 times 9.8 times 35 sine equals, we have a total force of 16.9, we'll say. 16.9 newtons. This is what's causing it to slide down. All right. Now, in order for the box to remain stationary, we need a force of friction that is at least equal to that. So force of friction. So if I want it to stay stationary, the force of friction must equal 16.9 newtons. Because we know my sliding force is equal to 16.9 newtons. So I need a force of at least that much, 16.9 newtons. How do I go about figuring out the coefficient now? Well, if you remember, force of friction, just going to slide this over a bit. Force of friction is equal to mu times Fn. And what was Fn? Well, Fn is just the amount of force that is compressing this box to the surface. In this case, it's no longer gravity, because gravity acts down this way, right? Gravity is not really compressing it against the surface. What's compressing it against the surface is this. Whoops, let's just cheat. Is this? That's what's compressing it against the surface. And now you can sort of see why we needed that. We called it the compressing force from the previous slide. So force compress. Okay, so to calculate the force compress, well, if you will just pull the formula from the previous example, Fg times cosine theta. So this will be 3 times 9.8 times cosine 35 equals, so pull out the calculator, 3 times 9.8 times 35 cosine equals, so 24.1. 24.1 newtons. That's my compressing force. Now I can put it into this formula. So I can say my force of friction is 16.9 newtons. We don't know what the coefficient of friction is. And the compressing force is 24.1 newtons. Okay. Alright, So then we've one step later, we'll divide both sides by 24.1. So we get our coefficient of friction is equal to 16.9 divided by 24.1. Oops, 16.9 divided by 24.1. There we go, 0.81. 0.81. There's my coefficient of friction. Okay. So now our normal forces, for at least for sloped surfaces, our normal force is no longer just the force of gravity, but still maintains the same definition, where this normal force can always be thought of as the force pressing or compressing two surfaces together. Compressing the surfaces together. Okay. It's handy to think of it that way, and then the force diagrams are easier to work with. Right. There we go. All right. Okay. That's the last example for today. Your assignment is as follows. And remember, let's see, you guys have your vectors test not tomorrow, but the day after. Yeah, tomorrow will just be review and then an activity to help solidify your concept of vector addition. All right, have at it.